Welcome to all dear students in Gokul Global University. Today we discuss about the topic UV spectroscopy, which is also means ultraviolet spectroscopy. Okay, there are three questions regarding to UV spectroscopy. The first is, what is UV visible spectroscopy? So here answer is molecular spectroscopy that involves study of the interaction of ultraviolet visible radiation with molecules, which means the particular molecules reacted with UV light and get excited and give the spectra. Now the second question is, what is the result of interaction of UV visible light and the molecule? Then the answer is ultraviolet light and visible light have just the right energy to cause an electronic transition of electron from one filled orbital to another of higher energy unfilled orbital. Okay, when a molecule absorbs light of an appropriate wavelength, an electron is promoted to a higher energy molecular orbital. The molecule is then in an excited state. That means when molecule getting energy by the UV light and goes to ground state to excited state, it means transition process occurred. Like this molecule is now in present in the ground state. After that, accepting the energy by the UV light and goes to the higher excited state. Okay. Now the third question is, what is the information you get from UV spectroscopy? The wavelength of absorbed light will provide the information on the energy gap which is related to functional group. So, by UV spectroscopy, we get very broad data and information about of compound. Now the second slide. So why we use UV spectroscopy? The first is detection of functional group. By UV spectroscopy, we get more information about particular functional group. Now the second is detection of impurities. Third is qualitative analysis. Fourth is quantitative analysis. So what is the difference between qualitative analysis and the quantitative analysis? So qualitative analysis means the analysis of compound in criteria of such a bond, molecule type, structure, etc. And in qualitative analysis, we analyzed the number of bond, molecule, etc. in compound. The fifth is single compound without chromophore. The sixth is drugs with chromophoric reagent. The seventh is it helps to show the relationship between different groups. It is useful to detect the conjugation of the compounds. The conjugation is the main phenomenon of this spectroscopy. Now here we give the electromagnetic spectrum. In this diagram there are many ranges given for different spectra region like X-ray, UV, visible, IR, etc. So here the visible spectroscopy. Here in given diagram, different range is given for different colors, and also look that white light in dispersed in 7 colors: red, orange, yellow, green, blue, indigo blue, and the violet. Now here the instrumentation of UV spectroscopy. The first is the part of the instrumentation of the UV spectroscopy is radiation source. So here the radiation source give the UV radiation, and it's monochromatic by the monochromator, and the divided by the beam divider. Then one rays go to the blank and the detected by the blank detector, and the second beam is goes to the sample and the detected by the sample detector. After both data goes to the amplifier and they goes to the recorder, and in the end we also get a UV spectrum. So there is a one law which is related with the UV spectroscopy. The name is Beer-Lambert's law. At a given wavelength, absorption is proportional to the concentration of absorbing molecule and the path length of the light through the sample. So here the equation of this law is log 10 IO upon I is equal to epsilon LC. Here A is equal to absorption of the sample is equal to denoted by the log 10 IO upon I. IO means intensity of the radiation entering the sample. I is equal to intensity of the radiation emerging from the sample, which means passing through the sample. L means length of the light path through the sample in centimeters. C means concentration of the sample in moles per liter. Epsilon means molar absorptivity. Okay, the intensity of an absorption band in UV is expressed as the molar absorptivity at maximum absorption lambda max. Now the some limitation of this laws. The limitation is the real limitation of the Beer's law is successfully in describing the absorption behavior of dilute solution only. In this regarding, it may be considered as a limiting law, as degree of interaction depends upon the contraction. The occurrence of this phenomenon causes deviation from linear relationship between absorbance and contraction. Now the principle of UV spectroscopy. Here we explain ultraviolet absorption spectra arise from transition of electron with in a molecule from a lower level to a higher level. A molecule absorbs UV radiation of frequency. The electron in that molecule undergo transition from lower to higher energy level. The principle of UV spectroscopy says that the molecule get energy by the UV radiation, absorb and goes to excited state from the ground state. Now we also the energy calculated by the equation E1 minus E0 is equal to HV. Then E total is equal to E electronic plus energy of vibrational, E vibrational plus energy of rotational, E rotational. So also the energy decreases in the following order, which electronic, vibrational and the rotational. So here also we give the diagram of the different types of the levels. Here electronic ground state, this is electronic excited state. Electronic ground state contain three vibrational levels like V1, V2, V3, V4. Electronic excited state also contain vibrational levels V1, V2, V3, etc. Now the spectra of the UV. The absorption spectrum. The UV spectrum is also known as the absorption spectrum. When a sample is exposed to light energy that matches the energy difference between a possible electronic transition within the molecule, a fraction of the light energy would be absorbed by the molecule and the electrons would be promoted to the higher energy state orbital. A spectrometer records the degree of absorption by the sample at different wavelengths, and the resulting plot of absorbance A versus wavelength lambda is known as a spectrum. So here plot of absorbance A versus wavelength lambda is known as a UV spectrum. The significant features is lambda max, which wavelength at which there is a maximum absorbance, epsilon max, the intensity of maximum absorption. Here we also give a presentation of spectra. The ultraviolet visible spectrum is generally recorded as a plot of absorbance versus wavelength. The choice of the solvent to be used in ultraviolet spectroscopy is quite important. Usually solvents that do not contain conjugated systems are most suitable for this purpose. Means the solvent which not contain double bond or the conjugation system is most preferred for the UV spectroscopy. Here we also get an example of the acetone. There are two peaks, lambda maximum is equal to 195, the transition which occurred pi to pi star due to the double bond, and the lambda maximum is equal to 274 and to pi star transition due to occur by the lone pair electron. Lambda max is the wavelength where maximum absorption occurred. So we have a different type of the transition occurred in the UV spectroscopy. Electronic transition. There are different type of this transition, the sigma, pi, and non-bonding, pi star, sigma star. So in next slide we also discuss about the electronic transitions. The main important electronic transition which are the first from pi bonding orbital to pi star and the bonding orbital, which known as pi to pi star. From n non-bonding orbital to pi star anti-bonding orbital, which known as n to pi star. From n non-bonding orbital to sigma star anti-bonding orbital known as n2 sigma star. In alkanes compound we also shows that sigma to sigma star or n2 sigma star, usually weak absorbance. Now the table given below of absorption characterized of n2 pi star transition. So the compound shows the lambda max and the epsilon max which suitable with suitable solvent. The first is methanol, shows the lambda max 177, epsilon max 200, solvent hexane. 1 hexanethiol shows the lambda max 224 and the epsilon max 126 in solvent cyclohexane. Trimethylamine also shows lambda max 199 in with epsilon max 3950 in solvent of hexane. N-methyl piperidine also shows the lambda max 213 in epsilon max 1600 in solvent ether. Diethyl ether also shows lambda max 188 epsilon max 1995 solvent gas phase. Here only in gas phase. Methyl chloride also shows lambda max 173 epsilon max 200 in solvent which hexane. Methyl iodide also shows the lambda max at 259 and the epsilon max 400 which solvent hexane. Here the first transition sigma to sigma star transition. An electron in a bonding sigma orbital of a molecule is excited to the corresponding anti-bonding orbital by the absorption of radiation, which means the electron goes to the sigma bonding orbital to sigma star anti-bonding orbital by the excitement occurred by the UV radiation absorption. So, to induce a sigma to sigma star transition, it required large energy. So, here the example is methane, which contain a CH bond. Methane contain only single CH bond. It's undergo only sigma to sigma star transition only. It gives absorption maximum at 125 nanometer. The second transition is N2 sigma star transition. In this type, saturated compounds containing atoms with unshared electron pairs are undergo N2 sigma star transition, which means the electron goes to the non-bonding n orbital to anti-bonding sigma star orbital. It requires less energy than the sigma to sigma star type of the transition. Most of the absorption peaks appearing below 200 nanometer. In the presence of polar solvents, the absorption maximum tend to shift shorter wavelength. Here some example given. Example, water, ethanol is a example of the polar solvent. In this, the peaks in UV region relatively small. Example like methyl chloride, oxygen, nitrogen, etc. Now the third transition and the fourth, which combine with each other, N2 pi star and pi to pi star transition. Most organic compounds are undergo transition for N2 pi star and pi to pi star transition. In previous slide, we also see the presentation of the UV spectra with example of acetone, which also shows the both transition N2 pi star and the pi to pi star. So what is the reason? Because energies required for processes bring the absorption peaks into spectral region. Both transition requires the presence of an unsaturated functional group to be pi orbitals. Here some example. For pi to pi star, there are some examples: alkenes, carbonyl compounds, alkynes. For N2 pi star transition, carbonyl compounds. We also know what is the carbonyl compound. The compound which contain a carbonyl group like ketone, aldehyde, ester, carboxylic acid, etc. So there are four transitions. The first is sigma to sigma star, the second is N to sigma star, the third is N to pi star, and the fourth is pi to pi star. These are all transitions have specific requirements specific energies